Projectiles launched at an angle, also known as just enough right triangle trig to get us through some more complicated projectile motion problems. Until now, you've only solved problems that have a projectile launched horizontally. And in those cases, we've always had an initial vertical velocity of 0 in this equation. So for projectiles launched up or down at an angle, the initial velocity is not 0. Let's learn the right triangle trigonometry. I want to be really clear, this is a brief introduction. Geometry classes are going to learn this concept way more fully. Let's start with a case where I have an object launched up at an angle with a given speed and a given angle. And so I've sketched out a triangle here, and you can see that velocity and the angle. Projectiles move horizontally at a constant velocity, and the vertical velocity is accelerated. In the initial state, you'll have a sketch that looks kind of sort of something like this. I've got a cliff, I've got an object launched up at an angle. So how fast and at what angle it's launched are known in this scenario. We can break that down into components or parts that describe the horizontal velocity and the vertical velocity. And here's how to do that. First of all right triangles with a known angle are similar, meaning they're either scaled up or scaled down versions that maintain the same proportions. The ratio between any two side lengths then would identify a specific angle. Trigonometry ratios named sine, cosine, and tangent are ratios of any two specific sides. For example, the sine of an angle is the ratio of the side opposite the angle and the hypotenuse. Meanwhile, the cosine of an angle is the ratio of the side adjacent to the known angle and the hypotenuse. Now, if I set that up, the sine of the angle theta is the side opposite the angle over the hypotenuse side. I can rearrange that equation to solve for the opposite side. The vertical velocity is equal to the given velocity multiplied by the sine of the angle theta. And we can repeat that process for the horizontal side, where we're going to use the cosine ratio. Now I've gone ahead and written out the y and the x velocities, and you can use your calculator to actually calculate the components. Let's solve example problem 1 on the next page. Now I've sketched a right triangle with a ball thrown up at a 60-degree angle at a given speed of 21.7 meters per second. Sketching the picture, identifying everything, done for you. Solving for the horizontal component is step 2. V sub x is the given velocity, 21.7, multiplied by the cosine of the angle, 60 degrees. What do you get when you calculate that? I get 10.85 meters per second. Step 3 now, solve for the vertical component of the velocity. It's going to be 21.7 multiplied by the sine of 60 degrees. What do you get? I get 18.79 meters per second. Now that I know the two components, I could solve a problem using the constant horizontal velocity and the changing vertical velocity with this as the initial